we talked about data, and now let's talk about the models we can use to build a soft sensor. And this time we will talk about a very specific type of model, and very common right now and very popular, so-called neural networks. What is the idea behind neural networks? So the idea about artificial neural networks is originated from the biological neurons or models of the neurons. So the common model or very basic idea of the model is that you have several inputs, then you have your cell, your neuron, some sort of processing unit inside, and then you have an axon. It's like normally very long element that is connected to the dendrites or inputs, axon output, that is connected to inputs of other neurons. Here another one, and this has also neuron is connected, and so on and so on. Here we have also some axons from other neurons, and so on and so forth. So very complex structure. And based on this biological neuron, the scientists in early machine learning phase, they developed a model of an artificial neuron. The model also consists of inputs and outputs and some sort of processing unit in the middle, or transformation unit. So let's start from the left. So we have inputs. Let's name them x1, x2 and x3. For this case we have only 3 inputs. Then we have so-called weights. We will talk about them later, what they mean. Let's say we have 3 weights, and then we combine them. Combining, I mean like we find the sum of them. We multiply the inputs by weights here, and then we just find the sum of them. In this case it goes up to 3 of them. And then you apply also additional so-called activation function, and then we have our output. And let's say activation function g, and then we apply the activation function on this, and we have this one as an output of our artificial neuron. Let's consider it a little bit more in details. Why do we need activation function? What do we have here? And why, how it works. First of all, let's consider this part. So we have inputs, then we multiply it by some weights, and then we find the sum, and at the end we have this one. If we rewrite it, we will get this. So it's basically nothing than a model of linear regression. So, but instead of weights, we had coefficients. Here we have also inputs, weights, multiply them, and we get this. The problem with linear regression is linear. We already talked that the processes we have in chemical industry are very non-linear. It's very complex. And that's why we need some sort of transformation, how we can go from linear model to non-linear model. And that's exactly what activation function does. The biological idea behind is that as soon as you collect enough electrical impulses from other neurons, as soon as you reach a certain value, it's like activation value, and then it will go further. It generates a pulse to the next neuron, and so on and so forth. but it needs to achieve a certain value, and that's exactly how the activation function, also some of them will work. There are more advanced ones, there are more simple ones, but let's talk about the simple one. And first, and then exactly for this, if we apply this activation function, most of them are non-linear, and that means instead of like you convert your linear regression into non-linear regression. And that's why you need this activation function. Now, as soon as you have the model of one single neuron, you can build a model that consists of a lot of them. Not only you combine them, like for example, if we say it will be depicted further as this. It's a single neuron. We can say we have our model, we have also inputs. It might be a lot of them. And you have also your neurons. And every input go to each neuron. In addition to that, as we already have our bias, our intercept in linear regression, like the first term, some sort of offset here. So we have 1 and you multiply it by a certain value every time. In this case, we also have it, and it's called bias. So basically it's x0, which is 1 every time, but you have also weights for that. But the idea is you combine the neurons, you can increase the number of neurons per layer, but at the same time you can also increase the number of layers. They're also connected, like in the feed-forward neural network, artificial neural network we are considering right now. All of the neurons are from one layer are connected to the neurons of the next layer. And thus we can build very complex models. And that's exactly what we would like to do with neural networks. We also have outputs. It might be, for example, 3 outputs. It might be 1 output. It might be more outputs. And as you can see, the main advantage of neural network is you basically have unified elements, unified building blocks, but at the same time, you can combine them in a way that you can really describe a very complex processes. And that's the main advantage of neural networks. At the same time, usually you apply the same parameter estimation procedure to find the parameters, so weights of the neurons. And you can easily increase the number of layers, increase the number of neurons. At the same time, the rest will stay the same. If we consider this network, it will return us the real numbers. So basically it's for regression task, in this case 3-dimensional regression, multiple regression. But the structure, the idea of neural network is so unified that you basically can also apply it to build a classification model. For that, you add additional layer, normally it's called softmax, that will transform your outputs to values between 0 and 1. And most importantly, in a manner that the sum of all outputs, let's say have them here, that the sum of the outputs are 1. That means you basically return the probabilities that your certain data instance belongs to a certain class. And then if you would like to get this class from probabilities, you just apply argmax function that basically selects the class based on the probabilities and say, for example, the maximum value of them, and return the index of this parameter with the maximum probability. And now you have these neurons, and basically every layer, for every neuron here, you need to apply this transformation, you need to apply this equation, and then you can build very deep models that we will be talking about as we will talk about the deep learning. Let's go a little bit back to activation functions. As I already mentioned, we have different types of activation functions. There is also a linear activation function. So basically it's like a line. It might be, for example, something like this. For x, you have epsilon. Epsilon is like output of your activation function. X is an input. If you apply this activation function, the problem is your output will be also linear dependent on the input, but in this case we will get also linear regression. Because some cases you would like to apply, but mostly you would apply nonlinear activation functions. For example, if you're talking about logistic regression, we already talked about sigmoid activation function. Where basically you have the values from 0 to 1 as output, and you have your, like the middle of this S shape is in the point of 0. Then you also have a very interesting activation function. Basically it's also similar to sigmoid because it also has S shape, but it starts from -1 and goes up to +1. And point 0, 0, so it has a point in 0, 0. This is so-called tangents hyperbolicus. It's like more beneficial if you apply it on neural networks, especially if you normalize your data. If your data goes here from -1 to 1, then you would apply this function, and the same you expect that the features from one layer to another, they would also have this shape, like from -1 up to 1. The problem of those activation functions is that as soon as you have your input value too high, the gradient you would need to train your model is almost 0. It's like literally almost 0. And in the same here in the range if you have very small numbers. They said it's like a problem for training, and that's why to avoid this, some additional activations functions were developed. So you basically do not have, or you have an area or range where you have zero gradient, but only if you have your input value too low or below 0. So this activation function is called rectified linear unit or ReLU. And in this case here, doesn't matter how large is the input, you will have a certain gradient value that is the same every time. Now we talked about the activation functions, we talked about architecture, how we can make it complex, and to build very complex models to describe very nonlinear processes. But if you go further, I mean, if you have a lot of hidden layers, like the intermediate layers, they might be some problems. Mostly they're numerical problems, and the problems you need to solve during your training process, because you cannot train a very deep neural networks as you can train a very shallow neural networks. And exactly about those challenges and some techniques you can apply and you would like to apply to train your model properly, we will be talking about next time.